All right, everyone, it's Mr. Rops here.
Miss Bui?
And Mr. Walker.
All right, and so we're back to this problem here with water leaving our bathtub. If you remember from a few days ago, we had the amount of water in liters as A, and T was our time, and we had this data set at various times of the water leaving. And we had found our rate of change, or our slope, as negative 6.67, and we had interpreted it. Now what we're ready to do is we are ready to write an equation for this line. Okay, so how are we going to write this equation, Miss Boy?
So what is the first thing that we need to have to write an equation of any line?
Oh, I need, I know the answer to this one. This one is, I need a slope and a point.
Do we have the slope?
Yes. What is the slope, Mr.
What is
Walker?
the slope?
That is minus 6.67. That's
So
just a number,
our
liters per
slope
minute.
is negative 6.67.
Yeah.
And what else do we need to write an equation of a line?
We need any point.
Any point between A and T, or X and Y if you're going to go with Desmos.
Right,
So
okay.
what point?
Let's use this nice one, 2016 was our first one. I chose that one because there's no decimal places, nice numbers around.
Okay, now I think it should be 1620.
Ah.
Oh, yes. Good catch. Good catch. The 16 is our independent variable. Okay, so now we're going to use our formula like y minus y1, but we don't have y's and x's here. We have a's and t's. So a is our y value. So a minus a1 equals m t minus t1. And so our 16 and our 20 are a1 and t1. And then we're just going to compute that out. And we're going to multiply it all out and see what we get.
So A will be equal to negative 6.67t. I believe the y-intercept will
Is
be
106.72, but then we got to get that 20 over there as well.
so plus 20.
Uh-huh.
Negative 86.72.
No, 126.72, because the negative times a negative makes a positive, and bringing the negative
Oh,
over makes
yes.
a positive, so it's all positive.
Oh, good thing you're paying attention because I am not. All right, so now we have our equation for the line. And so we know that we can, if we take that, we can graph it and see what it looks like. Should we graph it in Desmos,
Yes.
see if we actually did it correctly? So
All right.
3 fingers. All right, so Desmos limitations, we can only use x's and y's. So y67x plus 126.72. Oh, I think I did it correctly
Ooh.
because it goes so nicely through those data points. So I think we're doing really well. Let's go back to our other scenario and see where we are. Okay, great. So now we have the next question is we have how many liters are left after 13 seconds?
So your time is 13 seconds, yeah?
Right. So if time is 13 seconds, I want to find the amount. So I can just take that 13 and plug it into my equation. So t is 13, and I gotta... And when we do that calculation, oh my goodness. That's tricky. Hold on, it's coming. I'm throwing it into my calculator now.
I get 40?
40.
Exactly?
Exactly 40
40?
liters.
Liters.
Super. And you can just throw that calculation into your calculator and you're good. And then it wants to know after 30 seconds. Well, if I type in 30, I get... If I type in 30, this is interesting to me. "30 seconds, I do this calculation, and I get negative 73.3. Huh? How can I have negative 73.3 liters? What's
Yeah.
going on, Miss Boy? I don't
What is
quite
it?
understand. Look at the graph and see if we make sense of what's going on. What's going on with this? If I go if I go 30,
Right?
and if I get negative 70.3, that from the line makes sense. But what's going on in the bathtub?
I've noticed something here that happens at 19 seconds.
Right. Well, this at 19 seconds, or almost 19 seconds, it's 0. What's that mean? Miss Boy, what happens there?
No more water left in the bathtub.
Oh, the tub is empty.
Right.
So does this value even make sense, this 30 seconds? Does this value even make sense?
No.
No. So after 30 seconds, I know there's actually going to be 0.
So what should we write down then for the value?
I think
We should write down
I think we should say, does it make sense? A is 0.
I think it's 0 liters,
0.
right?
0 liters.
Right.
Because you can't
Which
have...
is going to be the same as an hour later as well.
Right. Cool. All right. That's kind of interesting. You have to really understand what's going on for that.
Yep. So the next problem tells us to determine how many seconds will there be only 7 liters left in the tub. So what is given in this question?
7 liters. That is the A value.
There's a volume there.
Right. So A is 7. I want to find T. So plus 26.72. Want to do this graphically?
Sure.
All right. So let's go back to our graph. And let's go, will it do? If I go y equals 7, right here at the intersection, I know it's going to be at 17.949 seconds.
Great. That was
Super.
easy.
That was easy. So I can, T equals 17.97 seconds if my memory serves me correctly.
Or we could also solve it algebraically and we should get the same answer.
We should get the same. Either way is, so is one better than the other?
Nope.
Right. They're
One is
both.
more efficient than the other.
That's true. That was pretty, Desmos
Yeah.
is super fast efficient. All right. The next question says, state the intercepts as coordinates. Explain these values within context. So if I want to find the x-intercept or the t-intercept, how do I find the t-intercept?
Graphically or algebraically?
I don't know. Which way you would like to do it?
Well, we already did it graphically.
Oh, that's right. If I go over the graph, it was
It was
down
19,
there,
right?
19.
So how could we do that algebraically then?
Right, so if it's the t-intercept here, I know that the a value is 0. The a value is 0.
So A value is our dependent variable.
Right.
And what was the
T
X?
is going to be 19 seconds.
About 19 seconds.
Yep. So if we want to do it algebraically, it would be 0 equals
Right. So 0 equals negative 6.67
T.
plus
plus-
126.72. And so when you solve it, t ends up being 19.
Yep. So if I take 126.72 divided by 6.67, and that should gives me the value for t.
I'm pretty sure it's 19.
Yep.
Yep, I
What do
just
you have?
checked it.
Okay. So
18.999.
so 19 seconds.
So when the amount is 0, the time is 19 seconds.
Right.
So what's that mean? In context, it means so when it takes 19 seconds to empty the bathtub.
Yeah.
Right, and it takes 19 seconds to empty the bathtub. And to have 0 liters.
Okay.
Awesome.
Now, the reason I like the slope-intercept form is because you automatically get an intercept with
right.
that.
Right. We can see what the y-intercept or the a-intercept is, and that is going to be 126. And that happens when the t value is 0. So when time is 0, it's 126.72 liters. So that must mean, when time is 0, that must mean when the bathtub, when it was full, when it started, whenever time started. So basically the bathtub, the most water the bathtub had was 126 liters of water.
Right. So the tub had originally 126.72.
2 liters, exactly.
Which I think is a good point to bring up is why it's better from a water conservation to take showers.
Oh, super. Nice. Especially if they're fast, you turn the water off in the middle.
Yeah.
Soap up, and then,
And
that's
then
why I
rinse.
have
In
no...
5 minutes. Your
that's
shower
right.
should last only 5 minutes.
Oh, 2 minutes, I tell you.
2 minutes. All right.
Well, that's why I have no hair, so I can be more efficient with the shower, you know?
Okay.
All right, so construct a graph of this linear function. Well, we've already made the graph.
Yep.
Over here we see the graph, and it talks about a suitable domain. What's that talking about, Miss Boy? A domain.
So the domain are the x values or the independent values,
The independent x value. So this is time in this case.
right?
And so what values of time make sense for our problem?
Can we have negative value for time?
Yes,
Yes, but not
in
not
this case-
but not in this case because we filled up the bathtub and we pulled the plug at time equals 0.
Right.
Now, that might not have been January 1st, 1901.
Right.
But we can at least just call that 0.
Right.
Right.
And can we have and then further down when we have 20 seconds to have negative liters, that doesn't make any sense. So I think our domain is going to be from 0 up into this x-intercept of 19 seconds. And then it's a different function afterwards. So the suitable domain is going to be from t is going to be between 0 and 19 seconds. All right. And then finally, the last question, I think this is the last question, is the point 1240 solution to the linear equation we wrote. Explain how you know algebraic and graphically. Well, I don't even know what that means. What does this point 1240 actually even mean in this case?
Well, if you remember, the x is the time, so 12 seconds.
Okay, and then it must be 40 liters. So it's saying at 12 seconds there was 40 liters of water. And so they want to know if that's on the line. Well, if we look over here, over the graph, at 12 seconds, I think the answer is going to be no, right?
Yeah, that looks...
Because it's going to be more than that. I can look just visually and tell that. So graphically, that's what I can do right here. I can say when x equals 12, I see that it is 46. So that's graphically. If I want to do it algebraically,
I think we actually found the answer to that question because if you look at this question right here, we said that
oh, you have to be on the black part.
we said that after 13 seconds, there are 40 liters.
Ah, looky there.
Yeah. So that's how we show algebraically
Right.
that 12, 40 is not a solution because if it's 40 liters, then it should
13.
correspond to 13 seconds.
Yeah.
Super. So therefore, this is an underestimate of what's actually going on because
Right.
46 seconds is liters is what
Right.
it was.
And mathematically, the left side is not equal to the right side. It is an untrue statement.
Super. All right, so there's we go. We using math in the real world in our bathtub scenario. It's great math. Love it.